Welcome back. I'm Larry Atherton from Motion Software. In this video, we'll look at another way to model valve motion and cam timing by using Lobe-Profile data. We'll uncover why lobe profiles are unique and how you can obtain profile data for your engine project. You'll see in step-by-step detail how to load and use profiles in our simulations. Finally, we'll go over the benefits and drawbacks of lobe profile modeling. Then in part 2 of this video, we'll explore the best ways to fine-tune lobe profile cam timing to optimize engine performance. In previous videos, we've described a common way to model camshafts using 5 timing points for each lobe. We call this method 10-point timing, since 10 data points are used to describe the entire camshaft. But why only 10 points? It's because most cam manufacturers publish these 10 points of data in their catalogs and websites. The data typically consists of primary and secondary valve timing and lift data for the intake lobe and 5 similar points for the exhaust lobe. For simulation purposes, these 10 cam timing points can be stored in a single cam file. These cam data files are used by our software to mathematically regenerate the valve motion curves required to perform an engine simulation. While 10-point modeling works remarkably well, there are shape variations that cam manufacturers grind into their lobes that simply cannot be regenerated from only 10 data points. Lobe profile data solves this problem by increasing the number of data points from 5 per lobe to 360 per lobe. In other words, instead of reconstructing the lobes from 10 timing points, lobe profile data contains the actual shape of the lobe itself with 360 points of resolution. This allows the simulation to directly use lobe profile data to model valve lift curves. And while interpolation is required to determine additional data between each of the points, for the most part, the software simply uses profile data as is to model valve motion. This can improve camshaft modeling accuracy, especially for high-output racing cams, where trick lobe shapes may be used to wring out the last few horsepower. With lobe profile data, those grinding strategies will propagate directly into valve motion used by the simulation. At this point, you may be asking, why don't we use lobe profiles for all engine modeling? The reasons are, first, the additional 355 lift points for each lobe are often considered proprietary information by the cam manufacturer and are simply not available. While the data can be obtained by directly measuring the lobes using a cam fixture like this one from Audi Technology, you have to purchase the cam before testing just to get the lobe measurements. Second, since lobe profiles map out the exact lobe shape, valve timing is locked into the lift data, making tuning and modification of individual valve events much more difficult, but more on this later. With the basics aside, let's jump in and start using profile data in an engine test. We'll use Dynamation 6 to simulate a performance Ford 5-liter Boss 302 engine. We'll start off with 10-point cam data, then switch to intake and exhaust lobe profiles for the same camshaft. Here's the complete 5-liter engine model without camshaft data. As we've done before, we'll complete the buildup by entering 10-point data directly from the cam card. The cam is a Comp 35-518-8, a roller hydraulic mild performance grind with a suggested peak engine speed of 6,000 RPM. Gross lobe lift is 348 for the intake and 354 for the exhaust. Rocker ratios are 1.6 and lash is 0. We'll enter 6,000th inch primary valve timing of 29 for IVO, 65 for IVC, 77 for EVO, and 25 for EVC. Then the 50,000th lift to rise timing is 4, 40, 52, and 0. Now the simulation is complete. I'll set up a power curve comparison so we can view these results side by side with lobe profile data. To do this, select Quick Comparison, then Make from Current Test to save the horsepower results in the background. I'll also set up a side-by-side comparison of the intake and exhaust valve lift curves so we can directly see where the 10-point and profile data differs. Next, let's locate the intake and exhaust lobe profiles for this camshaft. Here is one of the lobe cross-reference spreadsheets included in our lobe profile library. By the way, the complete profile library package is included at no charge with DynoSim 6 and Dynamation 6 simulations. Now let's find the Comp 35-518-8 camshaft in the cross-reference listing. Here is the data we're looking for. It includes intake and exhaust lobe timing data. And here are the lobe profile numbers, one profile for the intake and one for the exhaust. The matching lobe numbers are 3632 for the intake and 3634 for the exhaust. To load these data files into the simulation and switch from 10-point timing to lobe profile data, start by clicking the Import Lobe Profile button in the camshaft category. And, if necessary, navigate to the Lobe Profiles ECP folder, then scroll down to select the 3632 intake profile. Since there are more than 7,000 lobe profiles included in this directory, you can make selection much easier by simply entering 3632 into the file name box. And if the profile file is in the directory, it will appear in a drop-down list. Just select the file name and click Open. Now the Lobe Profile Import dialog appears. You can learn more about the information presented here by referring to the Simulation User Manual, but for now, simply select the destination for the intake lobe lift data. In this case, select the Intake Non-VVT button. Next, enter the intake lobe center angle of 108 degrees from the cam card and click OK. Notice that the profile file name is displayed here, and the Modeled From field has switched from 10-point to profile. Repeat the same process for the 3634 exhaust lobe. While the exhaust center line is not supplied on the cam card, you can copy it from the camshaft category, or you can calculate it with this formula. Exhaust center line equals 2 times the lobe separation angle minus the intake center line. Here the lobe separation angle is shown as 112 degrees on the cam card. So 112 times 2 minus 108 equals 116, which is the exhaust center line. The simulation results using lobe profile data are now overlaid on the original 10-point horsepower and torque curves. The differences are less than 3%, and in this case, the 10-point valve lift curves produced slightly more power. For some insight into the cause of the power differences, let's look at the valve lift curve comparison. The 10-point lift curves reconstructed by the simulation, in darker color, versus the 360-point data shows they are almost identical. The power increase is primarily due to slightly different valve acceleration rates in the 10-point curves. This is a good example of the potential differences that can occur between 10-point modeling and actual lobe data. While the simulated 10-point valve lift was quite close to actual cam lobes, the slight differences in overall shape generated higher valve opening and slower valve closing rates. This produced a 2% increase in power over the lobe profile simulation. Now let's review the rest of the camshaft category to see what other changes have been made to accommodate lobe profile data. In the cam and valve lift area, you'll notice that you can still enter rocker ratio and lash, but lobe lift cannot be changed. This is because lobe lift is determined entirely by profile data. If we change these values, the simulation would no longer model the imported lobe profiles. And for the same reason, primary and secondary valve timing points are also locked. However, the intake and exhaust center lines can still be modified, since these change the relationships between the intake and exhaust lobes, not lobe timing itself. Finally, the multi-lift calculator isn't available with profile data, since you never need to calculate timing at other lift heights. In fact, low-profile data can be considered a table of lift heights and timing specs for all points on the lift curve. So what can you do if you want to experiment with valve timing when using lobe profiles? We'll delve deeper into this in the next video. But in a nutshell, by converting lobe-profile data to 10-point timing, you can easily modify any cam spec you wish. Just press one or both of these to 10-point buttons to complete the conversion. That's it for Lobe-Profiles number 1. As I've mentioned, our Lobe-Profiles 2 video will pick up where we left off here and show you how to optimize profile files and to automatically tune cam timing for any engine using an iterator, a powerful tool built into our simulations. Make sure you get the complete story of profiles by watching part 2. If you have any questions or suggestions, please let us know in the comments section below. And if you have a cam you would like to see modeled, send a clear photo or a PDF of the cam card to support@motionsoftware.com and we'll share it in an upcoming video. Also, please like and subscribe to keep the tech information coming. We'll end with some more camshaft insight by David Vizard, who gained his knowledge from years of racing countless minis and small block Chevy hot rods. This time he reveals the most important valve timing event. See you next time.
During World War II and the time leading up to it, the aircraft industry did an immense amount of testing on camshaft valve events, and the general consensus of opinion by even the late 40s is that the point the intake valve closed was the most influential in terms of where power occurred in the RPM range and by how much. But like anything, when you think you've got a clear-cut picture of it, you find that things move on and something changes in the equation, and that changes what you thought you knew about it. And that's exactly what's happened. Although you'll find there's many fine books there by engineers who were top of their field at the time, are saying that intake valve closure is the most important aspect. We find that with today's modern high-performance engines and the science that we've managed to put into exhaust, that's now no longer the case. In reality, the most important thing is the amount of overlap when the intake is still open and the exhaust is on its way to closing, and there is an interaction between the exhaust system, the combustion chamber, and the intake due to pressure waves. That now has to be an appropriate duration between the two for the overlap, and it has to occur in the right phase. And when that's done, we're actually artificially applying a measure of supercharging to our engine. With both valves open, the exhaust can scavenge the chamber and start the intake charge coming in. So it's now filled the combustion chamber up, and at that point the piston is not even started to go down the bore. To give you an idea of how important this overlap area can be, is that on a typical 2-valve race engine, something like a NASCAR Cup car engine, the scavenging effect is so strong that the charge in the intake port is actually moving at over 90 miles an hour into the cylinder, and the piston's parked at top dead center. So what we have here is that the overlap in conjunction with the exhaust creates an entirely independent induction cycle. So our seemingly 4-cycle engine is now actually in reality a 5-cycle engine. That process has relegated the intake valve closure point to something like 3rd or 4th on the list of importance. It's still important. Every valve event is important. But if that overlap period is not utilized to its fullest extent, what can be given away amounts to a huge amount of power and torque.